This is first video on kinematics of rigid body. It's a conceptual video. Along with this video, you need to look at 3 other videos for mastering the topic for your exam purpose. Now, when it comes to kinematics of rigid body, you need to understand the 3 types of motions associated with rigid body. First one is called translation. Now, in order to understand translation, look at this figure. Here is a rigid body. It moves from position 1 to position 2. Look at the red line, red vertical line. Even if the body has moved to position 2, the vertical red line has remained parallel to itself. This type of motion is called translation. You can see it's essentially just dragging without any rotation. You just drag the cylinder along the surface. This is called translation. Next is rotation. Rotation is very well known. You know the ceiling fan? It rotates about the fixed point, something like this. This is said to be rigid body in rotation. And next is plane motion, which is essentially combination of translation and rotation. Look at this cylinder. Let's move it from position 1 to position 2. But see what has happened this time. The vertical red line has become horizontal. It means the cylinder has translated, like in first figure above, and also rotated at the same time, and that's why this vertical red line has become horizontal. This type of motion is called plane motion, and as you can see from this slide that it is essentially combination of translation and rotation. Now, our objective for this course, for this examination of Bombay University is very specific. It reads like this. You should develop capability of finding velocity of any point on the rigid body, which is in motion, the rigid body is in motion, knowing velocity of given reference point, meaning you will always be given velocity of one point and you will be required to find velocity of any other point. That's a specific objective, that's a specific capability which you need to develop. Let me take some number. In case of translation, let's say I have a cylinder whose reference point, that is the point whose velocity is known, I'm going to take as the center itself. Well, it can be any reference, but at the moment I am taking as center, and let the velocity of the center be 5 meters per second. Now, as the cylinder moves, velocity of center continues to be 5 meters per second, and let me find velocity of the top point. You know, it also is 5 meters per second. You know why? Reason is obvious. See, you are translated it, so you have just dragged it, and also the center and the top point are rigidly connected. So there is no reason for top point to any different velocity than the center point, and nothing else is happening. So that's the only velocity of the top point. In fact, when a rigid body is in translation, all the points on the rigid body has same velocity as the reference point. So to that extent, studying translation of rigid body is very simple. It's almost like treating it as a particle. Next is rotation. See, rotation is like rigid body rotates about some reference point. So from your knowledge of circular motion, you already know that, let's say, velocity of any point will be r omega. See here, if I am finding velocity of points on the circumference as shown, all of them will be r omega in different directions, of course. I am assuming the rotation to be clockwise. Suppose I want velocity of any inside point, then draw a concentric circle and velocity will be r1 omega, where r1 is the radius of this concentric circle. So that's how you find rotation, you find velocity of any point on the rigid body which is in pure rotation. Finally, let's talk of plane motion. Let's say this cylinder is in plane motion. Its reference point is the center, whose velocity is known to me as 5 meter per second. And let's also assume that angular velocity of this cylinder is known to me while it moves and rotates. Now look at the second position of the cylinder. Its center has velocity of 5 meter per second, and I am interested in finding velocity of one point on the circumference. Now this point must have 5 meter per second as one of the velocities, because point on the circumference and the center are rigidly connected. But mind you, this is not end of the story. This is not end of the story, because in addition to translation, it is also rotating. So due to rotation, that point will have velocity r omega, where r is the radius and omega is the angular velocity of the cylinder. And together, that is this phi the black velocity and r omega the blue velocity, together these two velocities, when you vectorically add them, that gives me the complete velocity of that point on the circumference. Now this aspect of two velocities and then combining them can be best explained if I take a numerical example. So let me take a cylinder which is in plane motion, that is translating and rotating, and let the radius of the cylinder be 0.75 meter. Let me take again the center as a reference point whose velocity is known to me, and let angular velocity of the cylinder be 2 radians per second. Now, this is the data, and in addition, of course, I must have velocity of the reference point, which is 1.5 meter per second. Now, this is the data. And what is my specific objective in this topic is to find velocity of any other point on this cylinder with this data. So let's say I want to find velocity of a point which has just come in on the circumference of this cylinder. Now, because the center, that is the reference point, and this point on the circumference are rigidly connected, one of the velocities which this point will have will surely be 1.5, the black velocity. But as you see, one additional red colored velocity is coming in. Now this velocity is come because while moving, cylinder has rotated with 2 radians per second. And you remember the last slide where that rotational velocity is r omega. R is 0.75, omega is 2, 2 into 0.75 is 1.5. And downward, because the way cylinder is rotating, you see clockwise, so tangent will be downward. And the point I am trying to make is, this point has 2 velocities, black velocity the translational and red velocity the rotational. Black velocity equals velocity of reference point, red velocity is r omega, and together, vectorically adding, is the complete velocity of that point on the circumference. Let's take the bottom point. Again, it should have 2 velocities, one the black one and another the red one. Only thing is, red one, that is the velocity due to rotation, is now towards my left, because if you see the tangent drawn and the clockwise direction, clockwise rotational direction of cylinder tells me that red velocity towards left, black velocity, which is velocity of reference, which is translational velocity, continues to be on the right. What is the net effect? Well, the bottom velocity, the bottom point's velocity is 0. At this instant, nothing wrong with it. Moment it goes ahead, this point will go up and it will have velocity. At this instant, this point has 0 velocity. It is, by the way, called instantaneous center. I'll elaborate it in the next video. But at the moment, we have found that the bottommost point has a zero velocity, which is very logical because after all it is touching ground and ground has zero velocity. So common point does have zero velocity. Let's take one more point. Say this. This should also have two velocities. One of them is 1.5 and another is red one r omega 1.5. And the top point similarly 1.5 and 1.5, this time both in same direction, so they get added. Okay. So the crux of the matter is any point on the rigid body has two velocities. One translational, which is same as reference, and other rotational, which is r omega. Let's say I want some point in between, say at a distance of 0.6 meters from the center. Then one of them has to be 1.5 and this one will be, this distance is 0.6, then this velocity will be 0.6 into 2, that is 1.2. And vector combination of 1.5 in x direction and 1.2 in direction perpendicular to the line joining center to the point of interest, that 0.6 length, perpendicular to that is red velocity r omega, and together that will be the complete velocity of this point. So what we have learned in this conceptual video is rigid body in plane motion has always two velocities. One translational, which is velocity of reference, and another rotational, which is caused by the rotation of the body above the reference, and which is always r into omega, where r is the distance from the reference to the point of interest. So this was the simplest possible example for the conceptual purpose. We will do more relevant examples from exam point of view in next 3 videos. Thank you.